Okay, so in this lecture, we're going to solve problems. So let's start with the last topic that we had discussed, that is polarization, right? So we have to show here basically Malice's law, right? Um, and to do that, recall that a polarizer essentially what it is doing is it is transmitting only the component along the component of the electric field, component of the E field that is along the polarization direction, right? So we are transmitting only that component of electric field that is along the polarization direction. So if I have a polarizer, let's say, right, and I have a particular polarizing axis here, right, and if I have a particular component of electric field that is this, and if it's making an angle theta, then what is transmitted is only E cosine theta. And like I said in the last lecture, instead of say having E along this direction, say if you have another E prime along this direction that's making an angle theta prime, then only E prime cosine theta prime makes it out, right? And as we have seen earlier, intensity of light, which relates to the electric field, is proportional to E squared, because the Poynting vector, remember the energy, the Poynting vector we defined is 1 over mu naught E cross B. That tells you how light is, the energy is transmitted with light. And also recall that B is much smaller than E, as E by C. So then you can write this as E cross E or E squared. So that's where intensity of light is roughly proportional to E squared. So if I have an intensity of unpolarized light, I naught here, then the intensity of light coming out on this side would be, I have to square this electric field. So I would get, I naught cosine square theta. Right? It's a simple division, and any proportionality factors would just be cancelled out because they are just constants. And so we would have intensity be square of theta, cosine square of theta, and that is what is called Malice's law. All right. So that's the first part of the problem here. So then let's look at the second part of the problem, right? So in the second part of the problem, we have two crossed polarizers, right? So crossed polarizers meaning I have a polarizer with, say, the polarizer A. Let's say the polarizing axis is along the y-axis. Then I have another polarizer B, right? So that's how the polarizer is, with its axis along that direction. This is another polarizer B, with its axis along the x-axis. So these are perfectly perpendicular. The question is asking what is the intensity of light as measured at the end of polarizer B. So we're measuring intensity of light at some point after B. So if light is incident on this, then this would ensure that polarizer A ensures that only the light along y-axis is going through. So whatever I get, it would be along the y-axis here. And this, because it's completely along the y-axis, and here the polarization is along x-axis, so polarizer B is only going to let such light which is along the x-axis through, right? So so this light would have no component along the x-axis, so none of the light makes it through. So you have zero, because the polarization directions are perpendicular. So when you are buying, for example, polarized glasses, that's what you could do. You basically take two of those polarized glasses, or which are claimed to be polarizing, and then you put them perpendicular to each other, and then the light you should see very less light. Now the second part of this question is, now we're going to insert another polarizer here in the middle. We're going to call it C. So we have another polarizer that is inserted in between A and B, and that makes an angle of 30 degrees. So this is 30 degrees with the first polarizer. Now what is the fraction of light that comes here? So let's say I have I, right? So if this is unpolarized light, here light is averaging, is basically oscillating every which way. So when you have unpolarized light, completely unpolarized light, go through any polarizer, you get half the intensity, because you are averaging the polarization along every which way, and when you average that, you get half. So unpolarized light going through any polarizer along any direction gives you half the intensity, I/2. And then we have this polarizing axis of C that's at 30 degrees, right? So then we have electric field along this direction for this light with intensity I/2, and that is at 30 degrees with the axis. So from Malus's law, I would get I/2 times cosine squared 30, right? So so I hope you're following me here, right? So cosine square 30, we can do some math, right? Cosine 30 is square root 3/2. So cosine square 30 is 3/4. So I would have I/2 times 3/4. But now this is at 30 degrees to the vertical axis, right? Because this C polarized it to go at 30 degrees. So I have 3I/8 is the intensity of light, and that is at 30 degrees to the vertical. That means it is 60 degrees to the x-axis. So whatever is the intensity of light here, that multiplied by cosine square 60. And cosine 60 is simply half. So cosine square 60 is 1/4. Or I can write this as 3I/8 times 1/4. Right? So then I would have 3I/32. Now it is not 0. Just because you inserted another polarizer in between, before you inserted polarizer C, the fraction of light that made it through is 0. But after you inserted a third polarizer C, it is not 0. It is 3I/32. That's almost 1/10 of the light, right? So that's a pretty significant part. That's 10% of the light compared to 0, right? So I hope you understood the problem here. First, unpolarized light gives you half the intensity, then 30 degrees. So you do cosine squared 30 again with I/2 as the incident intensity. Then you get 3I/8. Now you determine the angle between this light, which is now at 30 degrees. 3I/8 is at 30 degrees. And the next polarizer B is along x-axis, so the angle is 60 degrees there. You always have to look at the angle between the incident light and the polarizing axis. That is the angle theta here. So you get 3I/32 at the end. Okay. All right. So let's look at now a problem on the wave equation here. So here we have essentially the wave equation that we derived, right? So and what this question is asking us to do is, it is asking us to show that the proposition or the ansatz that this is a solution, right? So you can do that very easily, right? So you can just do dou E by dou Y. That would be E naught, right? Sine omega, right, t minus ky plus phi, some angle, right, times k in a negative sign, right? And if you do differentiation again, you would have the cosine back. So you would have minus k squared E naught cosine omega t minus ky plus phi, and this is nothing but again the Ey you started with. And if you do dou E by dou t, again you would have same thing. Instead here you have so here you would get a net, because this is negative, you would get a positive sign here, and because this is negative, again you get a negative sign. That's right. And here you would get negative omega E naught sine omega t minus ky plus phi, and if I do dou square E by dou t square, I would get again minus omega square E naught cosine omega t, and this is nothing but again Ey of t, but you have a factor of 1 by c square here, right? So you have 1 by c square here. So these two things will be equal only if k square is equal to omega square by c square, or k is equal to omega by c, right? Or I can write this as omega by k is equal to c. If I write what omega is nothing but 2 pi nu, and k is nothing but 2 pi by lambda, but it's in the denominator, so I would get lambda by 2 pi is equal to c, or 2 pi's cancel, and we have nu lambda, the frequency times wavelength of the light, is always equal to the speed of light. This is a direct consequence of the wave equation, right? And that should be the relationship between omega and by k, that omega by k is equal to c, right? Yeah, so this is called the dispersion relation. Dispersion relation is relating how the frequency and the wave vector are related to each other. Okay, so now we are going to discuss another thing, that is, what is the spatial and temporal evolution of a plane wave, like a cosine wave that we have seen. Like, so if I have E is equal to some E0 times cosine kx minus omega t, or omega t minus kx, it doesn't matter, right? So you know that the wave is sinusoidally evolving in time, and so it has sinusoidal variation in time, but it also has sinusoidal variation in space. So at a fixed time, even if I take it a fixed time, the wave has a sinusoidal space variation in electric field, right? So you have to think about both spatial and temporal evolution at the same time. So the pictures that are often shown in the textbook, like I have said before and even now, this kind of snapshots don't really do justice, because this is just one snapshot. So this snapshot is showing that electric field along x and y directions are varying sinusoidally, but the sinusoidal variation is also in time. So if I take several such snapshots, you get sinusoidal variation in several such snapshots as well, right? But a plane wave like cosine kx minus omega t, it does not, it goes to zero, but it does not fall down. It is infinite, right? Because it only oscillates between -1 and 0. It is not like it doesn't get damped and die away somewhere, right? It's infinite in extent and time. So it cannot describe something that's physical, right? A real physical wave like a pulse is described, like we have seen in the last lecture, a real physical wave is described by mixing various plane waves. So we're mixing various plane waves, and that's how we can describe real physical waves. All right. Okay. Now the next question is, let us assume a specific B component, right? Or E component, EY, and we have to find the corresponding expression for the magnetic field. So for this, you need to go back to the Maxwell's equation, right? That is, curl of E is equal to minus dou B by dou T, right? And if we just take electric field along the y-axis, if we pick electric field along the y-axis, it's only asking us to look at the magnetic field along the z-axis, and you know how to do the curl, right? So curl of E, you simply pick I, J, K, right? And the curl operator is dou by dou x, dou by dou y, and dou by dou z. And you have the electric field only along the y-axis, so EY, the other two things are 0. And we are only looking at the z component, only the z component of B, so only the z component. So that would be dou by dou x of EY and minus dou by dou of 0, right? So that is 0. So this is going to give you minus dou BZ by dou T, right? So you have the expression for EY, so you have to do dou by dou x. So if I do dou EY by dou x, that would be dou by dou x of EY0 cosine omega t minus x by c. Here we made it x by c because recall that in the previous question we derived omega by k is equal to c. So instead of writing it as k, we wrote it as omega by c. So this gives you k is omega by c. So then if I do the differentiation, basically I'm going to get dou by dou x. So I would get omega by c EY0 sine omega t minus x by c. Here the negative sign becomes positive because there is another extra negative sign. There is one negative sign from the derivative of cosine, another negative sign coming from this negative sign, and so it becomes overall positive. And this is what is equal to the variation of magnetic field in time, right? So if I integrate this in time, I should get the magnetic field back. And if I do the integration, right, I would have the other way around, right? And there is a minus sign here. So if I do the integration of sine, I would get negative cosine. So I would have negative 1 over c electric field times cosine omega t minus x by c is what I would get to be minus bz. So this minus and this minus cancel out, or you can see this is nothing but the electric field that we started with, or you can see how the magnetic field is electric field divided by the speed of light. Right? I hope that's clear. So I would suggest that you derive it yourself, and then you should be able to see what we're doing here. Okay, so next what we are going to do is we're going to look at different types of light and see how we can look at intensities, electric fields, and frequencies of light, how they to get a hands-on feeling for that. Right, so we are going to consider two laser sources. One is a helium neon laser at 543 nanometers. Another is a carbon dioxide laser that's at 10 microns, right? And both are with a power of 10 milliwatts each, right? So what we have to do is we have to calculate for each laser light the frequency, the wave vector, and the energy, and the intensity, right? So first let's let's look at the frequency. We have just derived the equation lambda times nu is c or speed of light, right? We derived this from the dispersion relation, omega by k is equal to c. So then we are given lambda for helium neon, that's 543 nanometers. We know speed of light, so the frequency nu would be c over lambda, or that is 3 times 10 to the power 8 meters per second, right, divided by 543 nanometers, that is 10 to the power minus 9 meters. And meters cancel out to give you units of 1 over second, which are the right units for nu. So that would give you 3 by 543 times minus 9. When it goes to the numerator, it becomes plus 9. So you get 10 to the power 17, 1 over second, and the unit for 1 over second is hertz, right? And if you do this 3 by 543, roughly you get something like 5.5 times 10 to the power 14 hertz, right? So that's the frequency for the helium neon laser. So that's the frequency for helium neon, because we had taken for the helium neon laser. Now if you look at the frequency for CO2 laser, right, it's again simple, right? So c by lambda, c is 10 to the power 8 meters per second, divided by lambda is 10 micrometers, so that's 10 into 10 to the power minus 6 meters, right? So that's 3 by 10 times 10 to the power 14 hertz, or that is roughly 0.3 into 10 to the power 14, or you can write it as 3 times 10 to the power 13 hertz, right? So we got the frequencies for helium neon and carbon dioxide using the dispersion relation lambda nu is equal to c. So next you can get the wave vector, right? Wave vector is very simple. Wave vector is simply k is equal to 2 pi over lambda. You are given the wavelengths. For one, the wavelength is 543. For the other, the wavelength is 10 micrometers. So it's very straightforward to do 2 pi over lambda. The only thing to bear in mind is when you are substituting the wavelength, please be careful about the units. This is nanometers, right? 10 to the power 9 minus 9 meters. This is micrometers, that is 10 to the power minus 6 meters. So you have to be very careful about the wavelength. Now then the next thing is we are going to calculate the energy. Recall what we had done in the beginning when we discussed light and quantum mechanics. that time we said that energy of light is related to its frequency through a fundamental constant, that's the Planck's constant. So E of this is equal to Planck's constant times the frequency. So you are asked to calculate in EV. So if you look at Planck's constant values, you would have that in either joule per second or EV per second, different units for Planck constant. So you pick the Planck constant value with EV per second, that is 6.58 into 10 to the power minus, this should be, I was wrong on the units of Planck's constant. It should be joule times second or EV times second, not divided by. So 10 to the power minus 16 EV second is the value of Planck's constant. And we have calculated what the frequency is, right? For example, if I look at helium neon laser, the frequency was, the one that we calculated was roughly 5.5 times 10 to the power 14 hertz, and hertz is nothing but 1/second. So then I would get energy to be Planck's constant in EV 6.58 into 10 to the power minus 16 EV second times the frequency, which is 5.5 10 to the power 14 1/second. So the seconds cancel out, and if you do the math, right, you would roughly see that this comes out to be 2.28 EV. So it comes out to be 2.28 EV for the helium neon laser, right? And then for the CO2 laser, you can do the same thing, and the energy for CO2 laser should be roughly 0.12 EV. The only thing that is different is the frequency of light. So the last thing that we need to do is the intensity in number of photons per second, right? So we basically know that the power is given to be 10 milliwatt, right? So we are given the power in the problem, and power is nothing but the amount of energy that is going through each second, right? So watt is joule per second, right? So, and if we know the energy for each photon, right, then basically we can calculate how many photons per second, right? But here we need to do a simple conversion, because the power is given to us in watts. So 1 watt, we have to convert that into electron volts per second. So we are given 10 milliwatts, right? This is 10 millijoules per second, right? And then you can convert joule to EV. Joule and EV are the same units that are measuring the energy. So 1 joule is roughly equal to 6.2 times 10 to the power 18 electron volts, right? And so that is equal to 10 times, milli is 10 to the power minus 3, and 1 joule is 1 joule is 6.2 times 10 to the power 18 electron volts per second. This is the power of the lasers that we have. So 10 to the power minus 3 and 10 to the power 18. So that is 18 plus 1, 19, minus 3 is 16. So I have 6.2 times 10 to the power 16 EV per second. That is the power. And for example, the energy of helium neon laser for 1 photon is 2.28 EV. So if I want the number of photons, right? If I want the number of photons, or that is what we call as number of photons per second, is what we call as intensity. So intensity will be equal to the power divided by energy per photon. And the power here is this. So because you're dividing, you just need to make sure that you have the same units. So the power is 6.2 times 10 to the power 16 electron volts per second, and energy per photon is, in case of helium neon, it's 2.28 eV. So eV and eV cancel, so you have roughly around 6.2 by 2.28, that gives you roughly 2.7 times 10 to the power 16 photons per second. That is the intensity of the helium neon laser. So we converted the power into electron volt per second first, and then divided with the energy of one photon, which is in electron volts. So we got number of photons per second, which is nothing but the intensity. You can do the same thing for the carbon dioxide laser for practice, right? Now let's see the electric field and magnetic field amplitudes, right? So here we have assume that you focus this light. You have this. You put some focusing optics. You put some lenses that we looked at to focus this light. For example, this laser beam is coming like this, right? And say you have a converging lens that's converging it to say 10 microns, right? So now we have to look at irradiance and or intensity, right? Intensity, we looked at intensity in the previous problem. We looked at it as number of photons per second, but you can also look at it from a power point of view. You can look at it as power per unit area, right? This is not this is power per unit area. That's also often called irradiance. Should not be confused with iridescence. So the irradiance of light is given by power per unit area. So here we know that we're focusing it down to 10 microns diameter, right? So the area of this spot would be pi times r square, that is pi times 10 microns is diameter. So I have 25, radius is only 5 microns. So micron is 10 to the power minus 6 meters. So r square would be 25 times 10 to the power minus 12 meters square, right? So that's the area. And the intensity, the power is 10 milliwatt. So the intensity for both lights, for helium neon, right, and for CO2, when they are focused down to 10 microns, right, because they have the same power and they're focused down to the same area, you should have the same watt per meter square. Roughly that comes out to be and this is 25 times pi times 10 to the power 12 minus 12 meters square. That comes out to be 12,732 watt per centimeter square. Okay, so now we can use this to calculate the magnetic field, the electric field, because we know that intensity is proportional to the electric field squared, right? So we know that intensity is equal to C times epsilon naught divided by 2 times electric field squared, right? And C, epsilon naught, 2 are all constants. So if you plug those constants n, you basically get electric field from the intensity. So you know the intensity, and you can calculate the electric field. The electric field would be roughly 3 times 10 to the power 5 volt per meter, right? So so the intensity, right, is the same, right, but the number of photons are different because the energy per photon is different. So if I look at the number of photons here, the number of photons, if you calculate for CO2 laser, it would not come out to be the same. It would come out to be an order of magnitude higher, because energy per photon in CO2 laser is lower. So it takes more photons to give you of CO2 laser to give you the same intensity, same irradiance than helium neon laser, for example, because the energy per photon is different. And the electric field is roughly of the order of magnitude 10 to the power 5 volts per meter, and magnetic field is roughly E by C, and C is 3 times 10 to the power 8, right? So this gives you a magnetic field of roughly 10 to the power minus 3 Tesla. This is a very, very weak magnetic field. For example, if you go to the MRI machine, you're talking about 0.1 to 1 Tesla, right? So this is a millitesla, which is very, very low, and you cannot really essentially differentiate it much from, I mean, on average, from the magnetic field of Earth itself. Okay. So so that is the thing about the electric and magnetic field amplitudes. So if you have any questions, I encourage you to please go back and forth in the video. Then the next part, we are going to look at phase velocities and group velocities. Recall, we discussed this very briefly when in the last lecture, that when you have two different types of electric field, they form what we call as beats, right? And we derived expressions for the phase velocity as omega by k, and the group velocity as d omega by dk. If you don't remember this, please go back and look at it again. So I can write the group velocity as d by dk of omega, but from here omega itself is equal to phase velocity times k. So then I could write this as d by dk times k times the phase velocity, because from here omega is phase velocity times k. Then if I differentiate this, I have d by dk by dk times vp by chain rule plus k times dvp by dk. This just gives me 1, right? So I would have vp plus k times dvp by dk, right? So now if you are going in some medium, then the phase velocity is essentially speed of light divided by the refractive index, right? So then I can write dvp by dk, this term, as d by dk of c by n, right? C is just a constant, so I can pull that out. So I can write this as d by dk of 1 over n, right? Or that gives me minus 1 over n square times c, right, times dn by dk, where n is the refractive index. Remember that refractive index is not a constant really. When we looked at the origin of refractive index and even before, we have seen how refractive index is dependent on the wavelength, and wave vector is nothing but 2 pi by lambda. So dn by dk is not just 0, it does vary with the wavelength. So now I can substitute this expression back in here. So if I were to do that, the group velocity is equal to Vp, the phase velocity, right, minus k times 1 over n squared c, right, c over n squared times dn by dk, right? But c over n itself is phase velocity, so I can rewrite this equation as the phase velocity minus k by n, and with one of the c by n's, I just left one n here, so I would have c by n left here. So with that, I can write another Vp times dn by dk. Or as we will write here, we can express group velocity to be phase velocity times 1 minus k over n dn by dk. But you know that k is simply 2 pi over lambda. So if I switch from k to lambda, I can write V group as V phase times 1 plus lambda over n dn by d lambda, right? The minus sign switches to plus sign, because if I do dk here, I would get minus 2 pi over lambda square d lambda, right? So dk is equal to minus something times d lambda. So that's why this minus sign becomes plus sign here. Now here we are given the wavelength dependence of the refractive index, that is given as some coefficient b, some empirical coefficient b and empirical coefficient c. So if I do dn by d lambda, I would get b is just a coefficient, so it is 0 minus, right, or plus c to the power d by d lambda of lambda to the power minus 2, or that is minus 2c, right, lambda to the power minus 3, right, or I would have minus 2c by lambda cube. So we got dn by d lambda. So group velocity here would be phase velocity times 1 minus lambda by n, 2c by lambda cube, or lambda and lambda cancel out here and you get a lambda square, right? So that would be v times phase velocity 1 minus 2c by n lambda square. And phase velocity is nothing but c by n, right? That is how much the velocity of light reduces. You're given the value of c and you're given the value of the wavelengths, right? And you know how n varies with the wavelength. So then you can make a table, right? You can make a table to show how these different wavelengths are varying, right? So recall that this equation is what we are using. So if I look at a lambda, a particular lambda, I can write what is that n for that particular lambda, and from there I can write what is phase velocity. Phase velocity is simply c by n. From there I can write what is group velocity, right? For that we will be using this expression where you need c, lambda and n for that lambda, right? So for example, if you take 400 nanometer light, you can put in you know the value of b, you know the value of c, right? You can plug them in here, right? And if you plug them in here, you can plug them in here and then substitute the answer here. So it would be a little more than 1.50 because you have a wavelength of 400 nanometers. So this term would add to 1.50, that is B, and give you a little more than that. So you would get 1.531. From there you can get the phase velocity, right? That would be C by 1.531, which gives you roughly 0.653 times C. And from here you can calculate the group velocity, that is this, and 0.632 C. So you'll always have a difference between group velocity and phase velocity in a real physical wave, because a real physical wave is not made up of a single sinusoidal wave. A real physical wave is made up of a composition of different physical waves, like we discussed in the previous questions. And because if you combine different waves to make a pulse of light, these different combinations would have different wavelengths. And because they have different wavelengths, they would have different phase velocities. And as a group, the entire wave packet will have a different velocity as a group, just like the marathon runners example we discussed while discussing group and phase velocities. They would have a different group velocity. So you can do for the other two wavelengths for practice, and for 800 nanometers, you would get something like 1.511. 0.662 C and 0.656 C, right? So you can do another question, that is find out the wavelength lambda where the group velocity would be equal to the phase velocity. Right, where the group velocity would be equal to the phase velocity. So you can find out that lambda. Okay. So now we're going to do one last problem from this is from one of the geometric optics example that we have studied previously, right? So here we have a biconvex lens. You're given the refractive index, and you shall have 10 centimeters in focal length, right? So you can use to see what is the radius of curvature. Recall the equation that 1 over focal length is the is n minus 1 by radius of curvature of the first phase plus radius of curvature of the second phase. But here we have a biconvex lens. That means the radius of curvature of this one is equal to the radius of curvature of the other one. So we simply have n minus 1, 1 over r plus 1 over r, or you have n minus 1 times 2 by r. This is equal to 1 over the focal length, or the radius of curvature then is simply equal to n minus 1, 2 times n minus 1 divided by the multiplied by the focal length. Multiplied by the focal length, right? You are given the value for n, you are given the focal length to be 10 centimeters, right? So that would be equal to 2 times 1.4 minus 1 gives you 0.4 times 10, right? That gives you 8 centimeters is the radius of curvature, right? So for the next part we have to draw the diagram. So you have the biconvex lens. You have the biconvex lens here, and an object is placed 2 centimeters in front of the lens. So you are given the object is placed here, and this is 2 centimeters. All right. So we need to basically make a ray diagram here, and to make the ray diagram, you know that essentially there would be one ray that is going to get focused, right? So that's going to get focused like that, right? And there is another ray that is going straight through, the center of the curvature. So if you extend these two behind this way, you would find that an image is here, right? So then we can use the equation 1 over f is equal to 1 over object distance plus 1 over the image distance, right? So you have 1 over 10 plus 1 is equal to 1 over 2, because the image object is 2 centimeters, right? And plus 1 over I. So then I would have 1 over I is equal to 0.1 minus 0.5, right? So, or I would get that to be negative 0.4, or the image is equal to 1 over negative 0.4, or that is 2.5 centimeters. So this would be 2.5 centimeters. So the negative sign here indicates that the image is also onto the left. Recall the sign convention, right? So the negative sign here indicates that the image is also onto the left, which we can see from the diagram. And you can also calculate the magnification if you want. The magnification is V by U, right? So you can calculate the magnification, or I by O, like how we had written here. So you can also calculate the magnification. That would be roughly minus 2.5 by minus 2. Minus and minus cancel, right? So roughly 1.2 times, 1.25 times magnification, right? Which you can see here that the image is magnified clearly, right? So these are the problems that I would like you to go through before the exam, so that you can prepare well for the exam. And yeah, I wish you all the best for the final exam. Please look at the email that I had sent earlier to see when the exam is, so that you have a good idea and there are no surprises at the end. So please go through all these problems once again. I will also upload a PDF copy of the PowerPoint. Thank you.